computer. Okay, I'll record it. I'll send this also
Thank
later.
you.
Okay, all right. So we need to do atomic structure, the trends. So I'm gonna bring up some problems over here. Hold on a second here. Let me see. Structure matter, outside possible set of quantum numbers. Okay, so we're gonna perfect. Okay, we're gonna quiz you on this here. I'm gonna put in the chat a file that I may have done before. This is a AP problems, but these are good problems over here.
Mhm.
Okay, is something coming through in the chat?
Oh yes, it says you shared a file.
Yep, and go ahead and open that up. And so I'm gonna share my screen. And the first section, structure of matter. This is perfect. Okay, we're gonna quiz you on all this. Yeah,
Wow. All right.
this is all exactly what we need. Um, all right. Advancing prison top right. All right, now the ones that I think that are possibly going to be on your test. Okay, so number 1, 3, 4, and 6. Okay, I want to do numbers 1, 3, 4, and 6. I'll skip the positive ion and the negative ion. Okay, so over here, questions 1 through 6, choose the answer below which best describes the direction of the various increasing trends.
Okay.
Okay, so atomic size. I'm going to stop sharing my screen. Is that okay?
Yeah, that's okay.
Okay. Okay, so here we go. This is just the trends. Atomic size. Again, we have a periodic table, and the question is, where are the largest atoms? Are they top left, top right, bottom left, or bottom right?
Was it bottom left?
Yep. Of all the atoms on the periodic table, francium is the largest of all. Atoms get bigger as you go down,
Mm-hmm.
but then they get smaller as you go to the right because you have a greater nuclear pull. Okay. Number 3, ionization energy. Where in the periodic table do the atoms have the highest ionization energy?
Um, does it go greater when it goes right?
Mm-hmm.
So would it be helium?
Yep. Right here.
Is it
So,
also like so it's right and up?
yep. So of all the elements, the ones that I want you to have in mind, helium and francium kind of goes like this.
Okay.
As you go to the right, helium is the smallest in size, and as a result, it's the hardest to ionize, the hardest to shake off an electron. When they say ionization energy, imagine you're holding an atom. How hard do you have to shake it for electrons to pop off?
Mhm.
So greatest ionization energy. And then over here, um, this is the largest size and the lowest ionization energy. All right. The next one, metallic character. Do you have a thought on that? I don't know if that came up explicitly in your notes.
Um, I'm trying to do it by memory. So, uh, was it like bottom left to
Yeah,
top?
that's going to be bottom left. When they say metallic character, metals want to lose electrons, and they're asking which metal wants to lose electrons the most readily, and it's going to be these in the bottom left here because these are the largest.
Oh, I didn't. I thought I was. I didn't know it. I didn't realize I'll get it right.
Yeah, that's when they, so that's what they mean by metallic character. When they say metallic character, that's synonymous with wants to lose electrons.
Okay.
Okay. And then the next one was electronegativity. And do you remember what electronegativity is? If I say to you, be very electronegative at school tomorrow, how are you behaving?
Would I be like by myself or
No, that would be the
social?
noble gases. They're by themselves.
Would I be like more social like
So electronegative means aggressive and pulling electrons.
oh
So of all the
so more
elements,
social?
yeah, of all the elements in the periodic table, fluorine is the most electronegative element of all. Fluorine is small, tight, and compact. Like if we were to compare lithium versus fluorine, right? If let's say we're to compare lithium versus fluorine, lithium has 3 protons in it, a first sphere, and a second sphere. Configuration is going to look like this: 1s2, 2s1, right? Fluorine is element number 9. Can you tell me the electron? So pop quiz, what is the electron configuration for fluorine starting with 1s2?
1s2, 2s2, 2p5.
Yep.
Whoa.
Excellent. Fluorine has 9, is element number 9, has 9 protons in it, and the electrons, the first 2 electrons are moving around in a spherical path, but that first sphere, I'm purposely drawing it smaller than the first sphere over here because we have a stronger nucleus. Right? Sucking everything in. That's the first sphere. The second sphere, here's the second sphere, also 2 electrons. Again, the second sphere there is going to be smaller than the second sphere over here. And then the p orbitals, and that's this thing over here. Now we're going to have electrons moving side to side, up and down, and front and back. Side to side, that's p sub x, up and down, p sub y, forward, front, and back, that's p sub z. And we're going to have an electron in p sub x, p sub y, p sub z, p sub x on the other side, p sub y on the other side, and we have an empty right there. So this fluorine is just missing just 1 electron, right? Here's the p sub x, p sub y, p sub z, up, 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 down, down. It's missing just 1 electron. And so if I say to you, act like a fluorine atom, you're going to be like tight and compact because you have a stronger nucleus, and you're missing just 1 electron. So you're going to want to steal an electron from someone else.
Oh, okay.
So as far as electronegativity goes, it increases as you go to the right, right? And it decreases as you go down. Because these want to lose electrons. They don't want to gain electrons. Now, the trend is towards the top right, but there's a trick here. The noble gases, these are completely filled. They're not going to be electronegative at all. So they have 0 electronegativity.
Oh, wait. So that's the exception?
Yeah. because electronegativity is how much it wants to gain an electron, and these are completely happy. They don't want to gain, so they have zero electronegativity.
Oh, okay.
Right. So now let me pop quiz you on some of the. These are the trends that you're going to have to be aware of here. All right, I'm going to clear the board. And I'm going to do a little summary type thing here. All right, let me clear this. It's all about periodic trends. Okay. So how do atoms behave? And this is the periodic trends. Here's an outline of the periodic table. As far as size is concerned, helium, smallest size, francium, largest size. As far as ionization energy goes, helium, hardest to ionize, greatest ionization energy. Francium, easiest to ionize, lowest ionization energy. And then electronegativity. So we have size, ionization energy, electronegativity. Did this term electronegativity pop up in your class?
Um,
It should have if he's talking about periodic trends.
I'm assuming he's gonna talk about. He didn't finish like the lesson yet, which is kind of strange because their next lesson is the day before the test. But I
Great.
feel like he will talk about it.
All right. Fluorine is the most electronegative. Electronegative means aggressive. Right? Aggressive. Wants to steal an electron. And francium is the least aggressive. Okay. So here we go. You're going to get questions of this nature over here. Pop quiz. Which has a larger atomic radius? And I'm going to pick a couple of elements over here. Silicon versus chlorine. What's your answer for that?
Silicon. Let me spot silicon. Okay, chlorine. So I would say that chlorine is smaller,
Yep.
so silicon will have a greater.
Yep. That's over there. Which has a greater ionization energy? Zinc versus phosphorus.
Zinc. Zinc. Where is zinc? I think.
Zinc is element number 30.
Oh. And phosphorus. Oh, phosphorus has a greater ionization.
This one has a greater ionization energy. And then rank from least to most electronegative. neon, calcium, bromine. Okay, which one of these is the least? Which one's the most?
Okay. The least. So neon is there. Oh wait. Neon is gonna be 0 electron.
Yeah.
So neon is least.
Yep.
And then now I just have to compare calcium, bromine. And then bromine's more electronegative, so calcium.
Mhm. Yeah, so okay, I didn't do it.
Oh wait, I
I
just
didn't do it. I just went like by the order of the numbers, but yeah, it ends up being that. Okay. Okay. Um, then go back to the file that I shared.
yes. Structure of a matter.
Number 7. I don't know if this word isoelectronic has popped up at all.
I don't think I've heard of it.
Isoelectronic means same number of electrons.
Oh,
Isoelectronic.
okay.
So like compare A and B, for example, like scandium with a +3 charge and chlorine with a -1 charge. Do they have the same number of electrons?
Scandium is 21.
Yep.
Right, and then it'll be -3.
Yep.
Wait, 21. Yeah, yeah. 21 -3.
Mhm.
And then which is 18, and then for chlorine, 17 plus 1, also 18. So,
So those are isoelectronic. And then you go through the whole process, but I don't think that may not be on your test.
okay.
We'll move
Good to
forward from there. Now, here we go. 13 and 14. I'm going to stop sharing my screen because I'm going to write on the board. Go ahead and read number 13.
Okay, number 13 says, how many lines are theoretically possible in the line spectrum of hydrogen from energies level N1 to N5? It's just 1, 2, 3, 4, 5.
Mhm. So you have an atom over here, and then like n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. And remember all those calculations you did? This is the Bohr atom. An electron can go from the second level. It could be excited to the second level, and then it could come back down to the first level. And when that happens, a wave of light comes out. Remember those calculations?
Oh, yes.
Right? Or if an electron was on the third level and went all the way back down to the first level, that would release a stronger light, more energetic light. So that would release a wave that would like be like this. Or you could go from the fourth level to the first, or the fifth level to the first.
Even
No.
more.
In this case over here, though, there are multiple options. This one was a little bit more complicated, but the question was, how many different possible transitions are there? Well,
Oh, transition.
there's going to be a bunch of them. You can go from 2 to 1, 3 to 1, 4 to 1, 5 to 1, or
Oh,
you can go from 3 to 2, 4 to 2, 5 to 2.
oh gosh.
You see where we're getting at this?
Yeah. When they say lines, does that mean like how many transitions?
Yeah, how many transitions? There, there, there. Those are all the transitions that are possible.
Oh, I see.
Okay.
Interesting. When it said lines, I was like, what?
Yeah, that's what they mean. How many different transitions? So we got 4, 3, 5, 5, 10. Yeah, it's gonna be 10. All right. Number 14, is that a possible question on your test, you think?
Number 14. Yeah. I think it's part. We had something similar today. It's like if it's allowed or not allowed.
Okay.
Well, I know definitely C is not allowed.
Yeah, you can't have 1/4 of a spin.
Wait. So the first one says no. You can't have a 0.
Yeah, you can't, there's no 0 level. So A and C very quickly are out.
And then for B, I feel like this one works.
Yep.
Yay.
And this is one where I think I sent, did I do a video? Oh yeah, I did a video thing, right?
Oh, yes.
And here, quantum numbers outline. Yeah, something like this, right?
Yes.
Yeah, so yep, so you can use this as a guide, and the options included whoa. Yeah, so like 3, 0, 0, 1/2. That works.
Is that in one of the packets? Because I recognize it.
Yeah. And then, but like, yeah, so 3, 0, 0, 1/2. Like choice C, well, choice C is out, but like choice D, for example, that doesn't work because in choice D, 2, 2, 1. So second level means that you're talking about, yeah, 2, 2, 1. So second level is this, but then L of 2 would be the d orbitals, and there's no d orbitals. Okay. All right, let's close up shop on that. Let's go back to this thing over here. Number 14. Ooh, number 16.
Wow.
Okay, this is a good one. I'm gonna stop sharing here. This one's okay. For this one over here, okay, here's what I want you to do. Can you tell me the electron configuration for iron? Just regular iron, Fe.
1s2,
Uh-huh.
2s2,
Uh-huh.
2p6,
Yep.
3s2,
Yep.
3p6,
Yep.
4s2.
Yep.
Is it 3d?
Yep.
1, 2, 3, 4, 5, 6.
Perfect. Okay. So that's the electron configuration for iron metal.
Okay.
Now, they're asking for the electron configuration of iron that has a plus. Actually, they're asking, I want to do one that has a +2 charge.
Would I move left 2 times or like
So 1s2, 2s2, 2p6, 3s2, 3p6. Now I'm going to pause right here. All right, first of all, this is argon. So you could see, you might see it written like this, argon.
Uh-huh.
What am I going to do over here now?
Maybe 4s2, 3d4.
And that's what a lot of people will write down, but that's going to be incorrect.
Oh,
What happens over here is the fourth sphere is farther away than the d orbitals on the third level. So if I were to scribble and draw this atom over here, iron is element number 26, and you're going to have a first sphere, a second sphere, a set of p orbitals on the second level, and then a third sphere, and then a set of p orbitals on the third level, up and down, and then a fourth sphere. And then you fill up d orbitals, but the d orbitals are part of the third level. They're in this third level over here. So this is weird with metals, when you fill them up, you go a little bit out of order. But when you start shaking the atom and start kicking off electrons, the first electrons that you actually would reach in and touch and pull out are the electrons in the fourth sphere. So when you remove electrons, you always have to remove electrons from the outer level.
oh,
So Fe with a +2 charge is going to be 4s0 3d6. Like there's no, or just simply 3d6. Right?
that makes sense. So like with the higher energy level, I use that one.
What's that?
Like the energy, like that greater one I use.
Yeah, it's going to be just the one that's farther, the greatest n value. You start taking those away.
Okay.
A lot of students get that wrong.
And then if it was like Fe3 plus.
Yep, now then you start, if it's 3 plus, then now you're going to take away from here and make that a 3d5.
Oh, I see. Okay.
That's a 3 plus. Yep. Okay. On this handout, can you go to question number 20?
Yes.
Read that and I'll stop sharing.
20 says, what is the maximum number of electrons in the energy sublevel designated by the L quantum number of 2? So for that one, if the quantum number is L quantum number 2, that means it's in the d orbital.
Yes, very good. Very impressed. So L value of 2, this is my outline that I have. That means you're in the d orbital, whatever level you're on. And so they're basically asking you, like, how many electrons can you have in a set of d orbitals?
Oh, like 10?
Mm-hmm.
Oh. 4.
Yeah, that was like one of the questions on your homework, I think. Wasn't it?
Yes.
Yeah, it was something like that. All right. Let's see what else we have over here. All right, let's give this one's is a misprint on this one here. All right, that's enough of those. Okay.
Oh, okay.
All right, so let's make sure you can do some of the Bohr atom ones with the calculations. Okay. Okay. I want to do a conceptual one and then an actual calculation one. Okay.
All right.
So here's a conceptual question. This is the Bohr atom. We're talking about a hydrogen atom. And remember, the hydrogen atom, the electron could be in the first level, but it could be in the second level and the third level. And when it's jumping up and down, if you excite this electrocuted, the electron jumps up, but then it's going to go back down and release a wave of light, that kind of stuff, right? Okay, so here we go. A couple conceptual ones. Which electron transition releases a photon or a wave with greatest energy. And the options are going to be n equals 4 to n equals 3, n equals 5 to n equals 1, n equals 3, n equals 2.
I feel like it's not gonna be the eyes. Or like not that. But like bigger transitions create bigger energy.
Mm-hmm.
So be B.
Yeah, that was gonna be this one over here. So that was gonna be B. How about which electron transition releases a photon with not the greatest energy, but the longest wavelength? Which one of these is going to have the longest wavelength?
Does longest wavelength mean least energy?
Yep.
Oh. Would it be A?
Yep, A is the correct answer. Very good. Okay, and now let's say that we wanted to actually calculate a wavelength. So find the wavelength of photon. And okay, so you're okay with this. I'm going to clear the board. Is that okay?
Yeah, that's good with me.
Okay. So, because I want to draw a nice picture here. So let's say that we have an atom. And this is an excited hydrogen atom, where the electron is in the n equals 3 level. It goes back down to the first level, and it releases a wave of light. And the question is, what is the wavelength of this light? Now, we don't have to actually go through the whole thing, but do you know how to solve this? Like, what to do? And actually, on your test, is your teacher giving you any formulas?
Oh yeah, he's very nice about that. He's like, no memorizing unless you have to.
Okay.
So it will be, I use the Bohr equation with the, I think it's energy equals like negative 2.18 something something.
Joules. And then you're probably going to be given this equation.
Oh yeah, Z is the atomic number.
Yeah. So we're making it easy on you here. We're going to make this a hydrogen atom. So hydrogen atom.
Is one.
Yeah, Z equals 1. I could pick something else, but leave it. And then we're going to go ahead and get this answer.
So I would do the whole thing and then 1/3 squared. No, 1/1 squared.
Mhm.
Yeah, and minus 1/3 squared.
Do this math.
Yes.
2.18 times minus 18 times. So this is what you're going to get from that calculation. Now,
Mhm.
you want to find the wavelength. This is the change in energy, or in other words, the energy of a single wave. Now remember the negative over here. What is that negative? Like, what does that tell us? Like, why is that even there?
Is it saying it's releasing energy?
Yeah. Yeah. So the wave is coming out of the atom, and therefore the wave is going to be, hold on a second here. Yeah, so the wave is going to come out of the atom, and the energy of a single wave. So this is the change in energy of the atom, like the atom. So that's what, so this over here tells us that actually, in backtrack, technically, what we calculated here is that the atom lost energy. So this delta E, means that the atom lost energy.
No.
That's what this is telling us. So therefore, it lost this much energy. So the wave of light, or the photon, so the photon energy is 1.94 times 10 to the minus 18.
Yes.
And now what do we do to find the wavelength?
Do we use the equation E equals hc over wavelength? Is that?
Mm-hmm. Yep. Yep. Now, is your teacher going to give you that, or is your teacher just going to give you the two original equations?
I think he's just gonna give me the original equation.
These over here. Yeah, and then you can just rearrange this. So C over lambda is equal to the frequency. Wait, this is H nu, sorry. That's like that. This could go over there. And basically, yeah, so this is really handy. But if you're not given that, you just use both of these two equations.
Okay.
You know, rearrange this. And then you plug in. Now, if we put that in the calculator, this is the value that we get. And then your teacher oftentimes wants you to change this into nanometers.
Mm-hmm.
And you remember how to change it into nanometers?
Multiply by 10 to 9.
Yep. 1 meter, 10 to the 9th nanometers. And you'll end up getting 103 nanometers. Yeah.
Yay.
Yeah, you'll have no problem. Those just, just be patient. Don't mess up on the math. That's all.
Okay.
No problem with those over there. All right, so we're in pretty good shape then. You get the Bohr atom, you know your quantum numbers, you know some of the trends. Okay. I'm going to put some more problems, or make up some more problems, but before I do so, pretend you were the teacher.
Okay.
Give me a sample question that you think that you would put on the test. I don't know. Look at your notes, or maybe a homework assignment, or
Okay, let me
something
see.
that we didn't do.
Oh, maybe like a work function problem.
Oh, yes, a photoelectron spectrum. Okay. Okay, yeah, we'll do a work function problem. All right. Now, so this is what they call the photoelectric effect. Oh gosh, I'm getting really sloppy here. Photoelectric effect. And the concept here is that you can pick off electrons from metal atoms. For example, I have over here, I have a piece of aluminum, this, and if I shine light on it, it will start to lose electrons. But what kind of light do I have to shine on it, and so forth. So the common ones are something like this. Let's say I have a surface of a metal and I have sodium metal. And I have all these sodium atoms. And sodium wants to lose electrons, right? It has a pretty low ionization energy, but still, even though something wants to lose electrons, you still have to like shake it a little bit. You still have to kick it or electrocute it or shine light. You have to add energy to get that electron off. And so if I add a wave of light that's really weak, like this would be low energy light. Right, I'm the sodium atom, I'm holding on to my electron, and someone hits me from behind, but they hit me very gently. I'm just gonna hold on to this. But if someone hits me really hard, then I let go. So this would have no effect. But if I shine light that's like this, then this will kick an electron out and higher energy light. And so the question is going to be something high energy in, and that's going to kick that off. So you're going to get a question. I need to make up, I can't make up some numbers here. So work. Photoelectric effect. Okay, so here we go. Okay. So if the ionization energy of sodium is, now I'm not sure if this is going to be the right number or not, but 350 kilojoules per mole. Will photon with wavelength of 150 nanometers ionize Na, and if so, what is the velocity of the exiting electron? Because you guys had to do that too, didn't you?
Yes.
Right.
Hmm.
All right, so what's the strategy here, first of all, before we do these things?
Let me get some equations. Okay. Photoelectric effect. Since I know the wavelength, I can find the
Mhm.
wait. Oh yeah, I had the wavelength, so I can find the frequency first and then make, actually no, that doesn't make sense. Actually, the electron, well, so if the,
So there's a couple of things we need to find. We need to find the wave that's coming in, right? The photon. We need to find the energy of the photon, energy of the incoming photon. We also need to find the energy to ionize an atom,
oh,
right? Ionize the Na atom. This is the work function. And then we could find the energy of the outgoing electron. Like these are the three things that we have to find in order to do a problem like this.
okay.
And the first two, doesn't matter which order we do these two in, but we have to do these two before we do this third one over here. So how would you go about finding the energy of the incoming photon?
Oh, I had the equation E equals hc over lambda.
And you're going to be given H. (6.626 times 10 to the minus 34th joule seconds). You're going to be given the speed of light, 3.00 times 10 to the 8th meters per second. And you're given the wavelength, 150 nanometers. Are we okay now, or do we have to do anything else over here?
I think we're okay now. Actually, no. We need to make the nanometers into meters.
And 10 to the 9th nanometers is 1 meter. Maybe that cancels out. So we're going to do all of this. Get that answer, 6.626, 10 to the minus 34, 3 10 to the 8th, divided by 150, 10 to the minus 9. 1.33 times 10 to the minus 18th joules. This is the energy of the incoming photon. Right. So the picture over here, that's the energy in. Now we have to find the energy to kick off an electron.
Yes.
And they gave us 350 kilojoules to kick off 1 mole of electrons. So what are we going to do over here?
So first I make it into joule.
And then
1 mole becomes P over mass grams. Oh wait, no, joules per second.
And 1 mole would have 6.022 times 10^23 atoms. And so this calculation over here, 350 times 1000 divided by 6.022 10 to the 23rd. This comes out to be equal to 5.81 times 10 to the minus 19th joules to ionize a single atom. So if I'm that atom, someone has to hit me with this energy to lose my electron.
That's very strong.
So now, what is the energy of this outgoing electron? It's going to be the difference.
Difference in
between the incoming and what you need to kick it off. So now we have that. That. So the difference is 7.4 times 10 to the minus 19th joules. So this electron coming out over here has an energy of 7.4 times 10 to the minus 19th joules. Now, didn't your teacher in one of the problems ask you to find the velocity of it?
Oh, yes.
And
so do I use the, I know that kinetic energy equals 1/2 mv squared.
Yep.
And then I can find that by, I have the work function and the
Yeah, this is the energy of the electron. So yeah, this is just 1/2 mv squared, or do 1/2, this equals 1/2 mv squared.
Oh yeah.
Yeah, we just did the difference for that. And then
Yeah.
1/2 mv. So this is the energy. The mass of an electron is so I'm going to get that energy times by 2. And then the mass of the electron will be given to you on the test. It's like 9.11 times 10 to the minus 31st.
Yes.
Divided by 2 times 1.4 to the minus 18. So v squared and then 7.5. So, and all said and done, v is 1.3 times 10 to the 6th meters per second. Okay, yeah, I'm glad you brought that up. That's like the last kind of problem that was on the test.
Oh, I see.
Ooh.
Good. Wow. You did a lot today.
Yeah, no, we covered a lot, but it's all doable. All right. Okay, so we're gonna go ahead and so that's it for tonight. I want to double check. Actually, I'm gonna stop the recording.